Thanks, Dan, and thanks, Karthik. Thanks, Jimmy, for inviting. I say thanks because actually Karthik did a good part of my presentation, so that's amazing. Thank you. And I do like Karthik because he said something I'm going to reiterate, and he specifically said, put it out there and iterate quickly. So what I'm going to try to do today is give a different point of view to what Dan was saying about how do we systematically improve the models. Dan was focusing on the model itself, and he gave a few notions about data coverage and whatnot, but he focused on the world model. I'm going to talk about the data and how we actually address those things, and I'm going to try to give a different point of view of what happens if we put the model out there, AlphaSim or whatsoever, and how can we iterate as fast as and as efficiently as possible.
So if you could project a little bit, just a little loud.
Okay. I will try. Okay. Sorry about that. A little bit about myself and my journey at NVIDIA. Actually, I follow the what Dan was showing about Jensen. I started with perception, efficiency, and then I moved to perception for autonomous driving, end-to-end models. And at the moment, the team that I'm leading, the research team, is focusing on trying to jointly optimize infrastructure, data, and models for autonomous driving and broadly for physical AI. I'm not going to repeat this. Dan did a good job. What is physical AI and what not? Here are a couple of examples of robotics doing physical AI. At the end of the day, we perceive, we understand, we plan, we interact with the world. And obviously, autonomous driving is one of them. I think is one tiny step towards the more complicated physical AI. The reason for that is because ideally we do not interact with the world. We don't have to touch things, right? So that would be the ideal situation for autonomous driving. So, as Dan was saying, what is missing to actually put out there things that are reliable? And I think what we need to do, what we need to consider is safety, quality, reliability, and trust. And as Dan was also saying, one of the key factors is dealing with the long tail, right? Those rare cases, first, not infrequent cases, rare cases, how do we understand those? How do we manage to drive here and then we move to London, as Waymo has done, and we also can drive there? How do we drive in different weather conditions? And more importantly, how do we iterate and continuously develop our models as fast as possible? It seems quite obvious that if we manage to do reasoning, any reasoning-driven model is going to be a key ingredient for this, for keep developing these models, right? For reasoning, we actually put out there at CEPR last year a VLM that was able to reason in the car to try to understand and give explanations of what are the decisions that the car is making. And also, as Dan was saying, NVIDIA a few weeks ago released AlphaMayo, which is an ecosystem, in this case a VLA, from vision to actions, that is able to reason and produce actions for driving. So what are the two problems? And we have seen this before, right? So there are two things that are critical, and Dan was talking about simulation for overcoming one of them. And the two of them is we still depend on human demonstrations, and the data is a problem, right? On the human demonstration, the big effort, and also Dan was talking about that, is how can we reduce the dependency? And through closed loop evaluation, closed loop training, that is an effective way to reduce the dependency with what the human, like imitating what the human is doing, right? There's lots of work to be done there. What is the reward? What is the right way to assess how good the model is doing? The infrastructure for training specifically, that's gigantic effort that needs to be done. AlphaMayo AlphaMayo and AlphaSim is a first step, and there's so much more to do. The gap between sim and the sim to real gap. Dan didn't touch that, but actually that's still something that needs to be done. It's looking promising. There's so much work to be done there, and we still need to be way more efficient. Dan was talking about NeuRec. Here we have an example where actually we can create a digital twin of a scene, and we can plug into the trainer and generate variations, as many as we want, and use them for training. I don't want to talk about that today. Dan touched a few. I really want to talk about the data, right? When it comes to real-world data, we have a decent amount of data. It's not infinite, but this decent amount. And we have several sources, right? Any car company is out there collecting data. That's what we call data collection fleet. It's extreme high quality, it's very expensive. And then we have some other, let's say, the models that we deploy. That's the consumer fleet. There is a specific targeted collection data that we have. That's a specific data, high quality, very narrow scenarios. And then there's an interesting source of data on internet, dash cams, right? Everyone is having dash cams nowadays. Now the question is, how do we leverage all that data? Here we have one case of nudging around a car for driving, right? So we need to navigate around the car. This is an interesting case. Here's something from internet, a dash cam, where actually it didn't go well. This is not a self-driving, this is an actual driving situation. And obviously, though that was real data, and there's all the plethora of generated data that we can address, right? NVIDIA has put out their Cosmos Drive Dreams, which is a way to transfer and generate new data. In this case, it's for different scenarios. You have day data, you can generate night data, snow data, any other weather condition. So how can we integrate that? That's a good question, right? Now, when it comes to data, we have a gigantic pool of data, and for safety, the problem is to find that data that is going to make a difference. If we are talking about the long tail, how do we find the long tail? How do we find the data that we can learn from? And if we talk about simulate, how do we know what data do we need to simulate? Dan was saying, oh, we can generate gigantic amount of variations. Which ones? Of which scenarios should we generate data? Because it's very expensive, at least as today, right? So the point is, how do we effectively deal with this data, and how can we continuously improve our models to keep addressing the long tail? So what I'm going to do today is talk about two things that I think are critical for the next steps. First, set up the foundation. How can we use foundation models to understand the data? And once we have that, how can we use reasoning in the loop, and I will define the loop in a minute, to systematically improve our models? What I would love you to take home, if I can just 3 minutes of your attention. First, that these VLMs are extremely powerful tool to organize your data, that they provide a level of abstraction that for AI is very good, is very critical. And when it comes to what I would call the development flywheel, is a powerful way that we can leverage to generate safe and generalizable models. I think if we want to automate, reasoning models is a critical component. The sooner we put the models and start collecting feedback, the better. And we don't have to understand what we need to reason. We don't need to use similarity. We don't need to use correlation. We need to have causal reasoning to properly understand the loop. So let's start with the first part, the true foundation, right? Dan touched this. What is a good data set? We have gigantic amount of data. Now, the question is, I give it to you and I say, train your model. what are you going to do? The first things that we need to consider is how related it is to my task. Dan was saying, if I want to do this, that's the data I need to, right? Extremely oriented to the task I want. It needs to be large enough. The quality needs to be good. The less noise, the better, if possible. And has to have maximum coverage. What does it mean? That's a good question. How do we measure that? That's a good question. So what we have been working on is, can we actually traverse all data and describe all data with foundation models? And what we have been doing is, instead of putting these VLMs in the car, where there's a few things that we still need to work on, what if we use them on the data side? And the idea is very simple. Just get a video, throw it to the VLM, ask a few questions, and let the VLM understand and tell you what are the actions, what is happening in that video, in a text, right? If we have that, then what we can do, obviously, first of all, we can find data. But we can find data in a way that is going to be diverse, because text adds a level of abstraction that is the similarity is not discriminative. It's just an interesting level of abstraction. Here we have some examples, for instance, for cutting in situations in driving. We ask for cutting, and we can retrieve similar actions, but not content-wise identical, which usually happens with visual embeddings. Here we have another example of left or right turns, right? The same. The action is good. The similarity at pixel level is different. So with this, we can retrieve data. Now, can we select our data to maximize the coverage and try to get the best model out of it? Our idea is very simple. What we need to do is give a structure to all our data. So now we have a description. If we can put some structure, cluster that into similar scenarios, then we will be able to select the most relevant data from those, right? And the important thing is that as we have this textual description, now each cluster, each group of data is clearly identified. To do this, super simple. With the same as before, we have a VLM. Now we just need a text encoder, a clustering technique, and that's it, right? And as we can see here, this produces a pretty good job. It's completely unsupervised. It just off-the-shelf works. Then when it comes to selecting the data, obviously the centroids, the closer you are to the centroid of the cluster, the more discriminative you are with the other clusters. So that data is going to be more informative for you, right? Does this work in practice? Well, what we observed is that if we do this with our existing data sets large enough, right? So it's already a curated data set. If we use this method, what we can achieve is a 30% reduction in data maintaining the performance, which is very significant. And if now we use this method to keep adding data, what we observe is for the same budget, we get much better results. Now, what is interesting is training these models is extremely expensive. So if we talk about 30% reduction, we might be talking about millions of data, millions of dollars of cost reduction, right? So we need to start thinking at that scale. More importantly, what we found out is that with less data, our coverage is better because on the long tail, we are able to get better results. Which goes to the point that Dan was saying, more data does not mean better accuracy in the model. What we are doing here is stretching and maximizing the coverage and what we call train space, right? So we just understand what are the situations we need to cover, and our data points are spread all over the place. And that results in very good results. This is great, this is for training, and this is the foundation. So what is next? So this is the development loop. Closed train evaluation, closed loop evaluation, closed loop training. That's what I call inner loop development tool, what the engineers, what the researchers are going to do. One more interesting loop is what happens when we start testing somehow with guardrails or in a safe manner at a scale. We're going to start collecting a lot of feedback. How can we get some useful information from that feedback? If we manage to close this loop, we should ensure, or we can ensure, that our model is going to continuously improve. And if we can automate this process, then it's the holy grail, right? At the moment, unfortunately, this is what happens, and it is very expensive, right? So we have lots of disengagements, something goes wrong. This is for autonomous driving, but should not be only for autonomous driving. You can think of any model out there, right? You have a disengagement. Now, someone says, this is this type of disengagement. This is this type of disengagement. What happened? What we should have done, and now that we should have done that, how do we fix it, right? Now, there are so many challenges to automate this process. First, we need to detect what is suboptimal, what is an error, what is a mistake, what is an accident. We cannot do one by one, then we're going to go crazy, right? So if we have millions of cars out there, it's going to be millions of disengagements. So how do we scale this up? How do we make sure that what we are testing and what we are training, this no domain gap? And interestingly, I will talk about if it's an error, and our end-to-end models are usually based on imitation learning, there's a mismatch. So if I imitate the error, my model will fail. So we need to change that. So here is an example. We have a deployment error. We were trying to test our policy, and the policy does not detect. We are making a right turn. The policy does not detect the pedestrian, right? So what we can do with the basis that I shared before is we can describe with our VLM the scenario, and we can get the closest data to that, right? So the problem with that is that if we do one by one, we are not really finding patterns. And that's related to what Dan was saying with the world models, right? And I think that's related also to why do we need the pixel level, right? At the end of the day, what we want is to discard the nuances. The pixel level sometimes might be nuances. What we want is, what is the root cause of the failure? So we think that grouping errors should give us a better structure to what is the real root cause, rather than focusing on the nuances, right? And importantly, if we do this, what just describing and finding similarity, we're going to find correlations. We're going to find similar data, but not what is useful for training. So to solve the scalability, let's plug and play the method before. Let's cluster the data and find data that is similar. In this case, it's disengagement, so it should work. If we try that, and what we found is that the errors follow patterns, we can find data that is similar, and actually, if we put that in the training loop, we're going to see that the errors go down. So it works. You can scale. It can go reasonably well. Now, what happens when we try to describe this? What happens when we try to describe this section, right? The problem is now we need to understand, we don't have human trajectories, we need to understand what did happen in that situation and what should we imitate, right? If we only describe the error, what do we find? This is an example of the problem that we were showing before. This is a disengagement, is a suboptimal driving situation, and we want to correct it. If we describe this with a VLM, with a multimodal model, what we see is that the description is reasonably accurate, right? We are turning, and there's a person crossing. But this is not the data that we want, right? Let me give you a very simple example. If we have this targeted error where we are crossing, right, and there's a pedestrian crossing, which of the ABC examples do we actually want to retrieve? A? Do we care about A? Probably not, right? So we are turning right, the person is crossing in front of me, I don't care. What we really want is C. We want to stop because there's a pedestrian, so we should not go. And that means that we don't need correlation, we need causation. We need to reason on what did the model do wrong and what should do well. So here's again the example. So the data that we really, really need is this one, right? Where we have a group of people crossing and the car actually slows down. If we manage to find this data or describe this data, then we will be able to find it or generate it with any world model video generation pipeline, right? So this is what we're going to do instead, right? So in this case, if we want to, let's put the case of extreme situations, accidents, right? It's a powerful way to try to learn from mistakes from other people. So we plug and play a reasoning model. Is going to explain what did go wrong, what should have happened, and with what should have happened, we can now generate as much data as possible, variations and whatnot, add them to the training set, and move forward. What should have happened is what we call counterfactuals. The more, the better, right? You didn't yell to the car in front of you. There's many things we can do. Those are the counterfactual. The minimum change that will make a different outcome, right? And I think reasoning is a good way to get to that point. In the data generation pipeline, Dan was also talking about generate a large amount of variations. In our experience, there's a lot of magic behind the scenes, right? This is the pipeline that we have been using. So we have a description of the scenario. Then we have a traffic world model, a generative way to say, give me an intersection, a car is crossing, I'm slowing down, or I'm maneuvering behind the car. And then we pass that to a physics base to make sure that the physics are correct. And we pass that to Cosmos Transfer to put the skin, to put the actual appearance that we want. What we found is that the traffic situations, we need to manually filter those situations, right? There's so many variations that do not make sense, or they are not informative enough. So there's a filtering process there. And with Cosmos Transfer, we can generate so many variations that many of them have hallucinations, problems, pixel situations, inaccuracies that we also need to reduce and need to filter out. So here's an example, a practical example, right? The same accident as before, and we ask Cosmos Reason, what happened here? And the model is able to describe the scene, right? It tells us what is happening. It tells us that there's a crashing problem, and actually is able to somehow why there was a crashing, right? This is very powerful. Now the question is, how do we make this useful for training? So here it tells us the reason and what we should do if we want to avoid, in a reactive, in a defensive manner, the accident, right? We cannot control what the others do, but what we can control is how do we change our behavior to avoid the accident. And I think I want to think that all of us do that when we drive, right? So if there's a person that is not doing the right thing, we're going to protect ourselves, right? And with this, we pass that to the generation pipeline, and now we can generate a good amount of situations where there's a car passing, we slow down, let the car go, and we accelerate again. This data is going to be extremely useful for training our model. And here's one more example, again from an accident where we try to incorporate into a highway, and there's some funny situation with this pickup truck that, is doing up, boom, right? Again, we ask the model what happened here, and the model describes the scene and describes what happened, why did we crash, and importantly, what we should have done to avoid this accident. With that, in the data generation pipeline, we can integrate this into our models or into the pipeline and generate similar situations when there's like a merge between lines, and we can avoid the accident because we, as ego vehicle, slow down. So as a take-home message, it's amazing. There's so much to do on the data side and on the feedback loop, particularly on the deployment feedback loop. On the one hand, we need to keep understanding and organizing our data, particularly for training and understanding what's going on. And on the feedback loop side, it's not enough with describing what happens. That's good for retrieval, but what we really need is to reason and causality, the root cause. If we find the root cause, we're going to accelerate much more the deployment of any model, world model, or any other model that we are trying to put out there as a product. Thank you.